Before we begin this unit on exponential functions, let's fully recap some of the functions that we've discussed throughout this year. If you recall, when we talked about linear functions, there were several different forms for a linear function, such as slope-intercept form, where the line can be written in the form of y equals mx plus b, or the standard form, where a function can be written as ax plus by equals c. Or even point slope form, where a function may look like y minus y1 is equal to m times x minus x1. So while I say all these things, keep in mind that the equation y equals negative 2/3 x plus 6 is actually the exact same equation as 2x plus 3y equals 18. They show the same relationship between x and y. As a matter of fact, when x is equal to 3, y is equal to 4 in both of these equations. They have the exact same relationship between x and y. Similarly, I could say one in point slope form that is equivalent to both of these equations would be y minus 4 is equal to negative 2/3 times the quantity of x minus 3. And I can, again, plug in 3 for x and 4 for y to give me an equivalent equation here. So something to keep in mind is that we can use algebraic manipulation to change these equations from one form to another. The same can be said with quadratic functions, which we've already talked about. Don't forget that the quadratic standard form is y equals ax squared plus bx plus c. So just like with linear functions, if I had the equation y equals x squared plus 2x plus 4, and I wanted to complete the square within this equation, let's go ahead and make this 0. Change this function into an equation. And let's say I wanted to complete the square to solve this quadratic. Well, if I want this number to be 1 to make it a perfect square, I can subtract 3 from each side. And now that I have a perfect square, now that I have a perfect square, I know that this equation is equivalent to this equation, which is equivalent to my original equation. I've just done some algebraic manipulation to change them. But what's most important here is that I wanted to discuss the fact that while there is a standard form for a quadratic equation, and there is a standard form for a linear equation, we also have a standard form for our new topic of discussion, which we will call exponential. So the word exponential, you might see the root here is the word exponent. Some of you are looking back at this quadratic and saying, wait a second, quadratics have an exponent in them. Does that make them exponential? Actually, the reason these functions are called exponential is because the independent variable, x, is going to appear in the exponent. Right here you are looking at what we call the standard form for an exponential function. The one we're going to focus on here today is simply y equals 3 times 2 to the x power. Now the reason I brought up the many different forms and many different ways to represent an quadratic and linear functions is that you might see this grouped in many different ways, such as y equals 3 and 2x in parentheses. It's interesting to note here that every single exponential function can be written in this standard form. And just like any other function, we can have a series of inputs and outputs. I can plug in 0 for x and evaluate for y. And I can create a table of values to show the relationship between x and y. Let's take a quick peek at this one. For instance, if I wanted to evaluate 3 times 2 to the 0th power, again, don't forget that my order of operations are going to come into play here. This is why we discussed order of operations at the beginning of the year. They continue and continue and continue to show up. So if I evaluate 2 to the 0th power first, we know that anything to the 0th power is 1, and 3 times 1 will leave us with 3. So let's go ahead and evaluate 3 times 2 to the first, and 3 times 2 to the second, and 3 times 2 to the third, and 3 times 2 to the fourth. Again, remember to evaluate the exponent first. 2 to the first is 2, times 3 is 6. So when I input 1 for x, my output is 6 for y. 2 squared is 4, times 3 is 12. When I input 2 for x, my output is 12 for y. 2 to the third power, be careful here, because 2 to the third power actually means 2 times 2 times 2. 2 to the third power is 8, and times 3 is 24. You may be noticing a geometric sequence appearing here as I continue to multiply by 2 to find the next number in the sequence. So you can imagine that this next number is just going to be twice the previous output. 2 times 24 is 48. So 2 to the 5th times 3 should give me twice that number, 96. So in class we're going to make this connection here between geometric sequences and exponential functions. Just like previously when we talked about arithmetic sequences and linear functions, there is a connection between a geometric sequence where we continue to multiply by a constant ratio to find the next term in the sequence. And it's no coincidence that this number here is 2. As a matter of fact, we are going to discuss what each part of this exponential function represents in class tomorrow. Just like when you looked at linear functions and you knew that y equals mx plus b, where m is the slope and b is the y-intercept, we will have very similar parts to our exponential function as well tomorrow. We'll also discuss how to graph exponential functions and what the graphs of exponential functions should look like. So there's a brief overview, kind of an introduction to exponential functions and something that you can expect to see in class.